Digital computing grew from a mid-century premise: two states, 0 and 1, false and true, inactive and active. When we attempt to build intelligent systems, a structural bottleneck appears. Intelligence doesn't operate exclusively in absolute truths. It requires the capacity to represent a not-yet-known status directly within the data. Standard machine learning architectures approximate this unknown state using floating-point math. They calculate continuous probabilities, relying on calculus to produce a best numerical guess. The Aurora architecture adopts a different foundation. It introduces a discrete third state, the number 2, which structurally represents indeterminate or pending resolution. In this system, the value 2 is a native computational state. It doesn't signal a crashed program. It functions as a physical control structure. This shifts computation from forcing a result to identifying exactly where information is missing. The value 2 identifies which relations remain open and where the system is still waiting for context. This chart shows the TriGate, the foundational logic gate of Aurora, starting with the ternary and function. It extends traditional logic to process zeros, ones, and twos natively. Observe the dominant 0 rule. If one input is 0, the answer resolves to 0 immediately. We don't need to know what the 2 will eventually become. In the next row, 1 and 2 equals 2. Because the result depends entirely on that unresolved value, the gate keeps the operation open. The ternary OR table demonstrates the inverse. 1 or 2 immediately resolves to 1, but 0 or 2 remains pending, holding the state until the second input is resolved. If the operator itself is indeterminate, the TriGate uses the unknown function. The output stays at 2 unless the inputs happen to match, forcing the gate to wait for more context. When a TriGate produces a 2, it enters a low-power standby mode. It does not recompute the same unknown relation. It waits asynchronously for an event to change a shared value. Computation changes from a rigid sequence of instructions into a propagation of coherence. Logic only resolves when the available information is sufficient to close the gate. If a TriGate stays in standby, it must still track the logic that originally constrained it. Aurora uses a secondary output, the coherent state, or variable E. This captures whether the relationship is direct or complementary. When the result is a 2, the E state acts as a carry, preserving the residual direction, ensuring determined information survives standby. Neural networks rely on calculus to navigate a continuous loss landscape. Aurora uses a discrete relational gradient, tracking direction using whole numbers, not floating-point estimates. As these E states aggregate upward through the system, they form probabilistic majorities. The architecture reaches conclusions based on which directional residue survives most consistently across the relational structure. This creates a learning system that doesn't minimize a numerical error function. Instead, it progressively resolves a discrete space until the network reaches a fixed point. This logic lives in the operational seed, Aurora's minimal data structure, a base triplet and one upper orientation trait. The third position, structure, is fixed. Function and form can exchange positions, while the upper trait reconstructs the semantic order. This is a homoiconic system. The ternary values used for data are identical to the values used to represent the logical functions operating on it.
The upper trit acts as active metadata. It allows the system to differentiate between an object and its function purely through its relational position. If a 2 appears in this upper metadata, the orientation itself is unresolved. The data becomes an active control signal, preventing the seed from resolving until it receives context. The separation between data and code disappears. In Aurora, the structural state of the information dictates its own computational path. Operational seeds recursively connect to form a larger structure, the fractal tensor. This hierarchy determines how meaning and uncertainty propagate through the system. The lowest levels hold relational details. The top represents the emergent semantic state. Uncertainty is filtered by relevance. If an unresolved bottom node cannot change the top result, the semantic state remains stable. Ambiguity only propagates upward if it alters the top-level meaning. This allows the system to reach a conclusion without perfect information. A tensor is coherent if its highest semantic meaning is invariant to the uncertainty remaining below. Aurora processes these tensors through a sliding window, which compares two known structures to resolve the unknown operator connecting them. Faced with an unknown operator, the system searches its dictionary. This ternary constraint graph contains crystallized relations, structures that previously achieved coherence. Logic defines what is possible, but the dictionary defines what is admissible. Aurora only closes relations using existing memory tensors. Search priority is governed by recency. Paths that successfully reached a coherent fixed point recently are tested first, accelerating retrieval in familiar contexts. Inference becomes a search for closure. The system cannot arbitrarily generate an answer. It can only conclude when logical possibility intersects with an admissible known tensor. If a node's local dictionary does not contain the crystallized relation required to close the tensor, it reaches its local coherence limit. Instead of failing, the unresolved state transforms the computation into a carry tensor. This preserves the exact residual state and open dependencies of the local problem. This initiates relational routing. The upper semantic structure of the carry tensor acts as a relational address, describing exactly what context is required to reach a fixed point. The carry tensor leaves the local node, traveling across the network. It bypasses generic hardware, seeking a specialized node compatible with its relational signature. Intelligence scales horizontally. Rather than building one massive centralized brain, Aurora routes unresolved dependencies to specialized contexts capable of providing the missing context. Once the specialist node resolves the dependency, the result returns to the original node. This event wakes the waiting TriGates, allowing the original computation to resume. When these events converge, the input, distributed knowledge, and output achieve total semantic closure. They satisfy every global constraint at once, reaching a fixed point. This same law dictates every scale of the architecture. Resolve what can be resolved. Preserve what remains open. Propagate the ambiguity. Intelligence becomes a dynamic search for coherence across every scale of computation. It is the process of resolving unresolved states until the relational structure is complete.